Today we're going to be building an LSTM in Excel. Before we build it though, I kind of just want to quickly go through what an LSTM is again for me, and then I'll try to explain it for you guys. Again, that video from Brendan Rower I think is phenomenal. So I'm just going to quickly give it another watch because there are a few technical stuff I just want to pick up on and see where to put them. But I need to get one. That's not what I came to YouTube for, but holy cow. Interesting. Anyways, I'm here to learn about, this is why I don't like YouTube that much.
The one that is true right now. Applications of and that you are every night pizza have for dinner our flatmate was in a late going to have highly recommend, and your all of the inputs like on your history of what you've had for dinner, and you learn how to predict what's going to be for dinner tonight. The trouble is that your network doesn't work very well. Despite carefully choosing your inputs and training it thoroughly, you still can't get much better than chance predictions on dinner. As is often the case with complicated machine learning problems, you do that. Then sushi doesn't depend on the day of the week or anything else. It's an irregular cycle. So knowing this, we can make a new neural network. In our new one, the only inputs that matter are what we had for dinner. sushi yesterday, waffling process, and it's right all the time. Now, if you happen, it is incredibly consistent. Now, if you happen to be gone on a given night, let's say yesterday you were out, you don't know what was for dinner yesterday. You can still predict what's going to be for dinner tonight by thinking back 2 days ago. Think, what was for dinner then? So what would be predicted for you last night? And then you can use that prediction in turn to make a prediction for tonight. So we make use of not only our actual information from yesterday, but also what our prediction was yesterday. So at this point, it's helpful to take a little detour and talk about vectors. A vector thing, and we go through the dinner tonight. We said everything equal to 0 except we can group together our. Now we can group together our inputs and outputs into vectors, separate lists of numbers, and it becomes a useful shorthand for describing this neural network. So we can have our dinner yesterday vector, our predictions for yesterday vector, and our prediction for today vector. And the neural network is just connections between every element in each of those input vectors to every element in the output vector. And to complete our picture, we can show how the prediction for today will get recycled. The dotted line there means hold on to it for a day and then reuse it tomorrow. And it becomes our yesterday's predictions tomorrow. Now we can see how if we were lacking some information, let's say we were out of town for 2 weeks, we can still make a good guess about what's going to be for dinner tonight. We just ignore the new information part and we can unwrap or unwind this vector in time until we do have some information to base it on, and then just play it forward. And when it's unwrapped, it looks like this. And we can go back as far as we need to and see what was for dinner and then just trace it forward and play out our menu over the last 2 weeks until we find out what's for dinner tonight. So this is a nice simple example that showed recurrent neural networks. Now to show how they don't meet all of our needs, we're going to write a children's book. It'll have sentences of the format, Doug saw Jane, period. Jane saw Spot, period. Spot saw Doug, period. And so on. So our dictionary is small, just the words Doug, Jane, Spot, saw, and a period. And the task of the neural network is to put these together in the right order to make a good children's book. So to do this, we replace our food vectors with our dictionary vectors. Here again, it's just a list of numbers representing each of the words. So for instance, if Doug was the most recent word that I saw, my new information vector would be all zeros except for a 1 in the Doug position. And we similarly can represent our predictions and our predictions from yesterday. Now, after training this neural network and teaching it what to do, we would expect to see certain patterns. For instance, anytime a name comes up, Jane, Doug, or Spot, we would expect that to vote heavily for the word saw or for a period, because those are the 2 words in our dictionary that can be on the previous time step. We would expect those to vote also for the word saw or for a period. And then by a similar method, we'll learn strongly for a name, Jane, Doug, or Spot. So in this form, in this formulation, we have a recurrent neural network. For simplicity, I'll take the vectors and the weights and collapse them down to that little symbol with the dots and the arrows, the dots and the lines connecting them. And there's one more symbol we haven't talked about, how it works, squat out. Negative, a loop like this, 1 and 1. So this is really helpful when you have a loop like this, where the same values get processed again and again, day after day. It is up to be at -1. Feedback loop, this is an example of negative feedback or attenuating feedback. So you may have noticed our neural network in its current state is subject to some mistakes. We could get a sentence, for instance, of the form, Doug for the word saw. Because each of our predictions only looks back 1 time step, it has very short-term memory, then it doesn't use the information from further back. And it is subject to these types of mistakes. In order to overcome this, we take our recurrent neural network and we expand it, and we add some more pieces to it. The critical part that we add to the middle here is memory. We want to be able to remember what happened many time steps ago. So in order to explain how this works, I'll have to describe a few new symbols that we've introduced here. One is another squashing function, this one with a flat bottom. One is an X in a circle, and one is a cross in a circle. So the cross in a circle to the first equals 11. Number multiple, very closely related, gives you the same size. Multiplication lets you do something pretty cool. Now, element-wise multiplication lets you do something pretty cool. You imagine that you have a signal, and it's like a bunch of pipes, and they have a certain amount of water trying to flow down them. In this case, we'll just assign the number to that of 0.8. It's like a signal. Now, on each of those pipes, we have a faucet, and we can open it all the way, close it all the way, or keep it somewhere in the middle to either let that signal come through or block it. So in this case, an open gate, an open faucet would be a 1, and a closed faucet would be a 0. And the way this works with element-wise multiplication, we get 0.8 times 1 equals 0.8. That signal passed right through into the output vector. But the last element, 0.8 times 0 equals 0. That signal, the original signal, was effectively blocked. And then with the gating value of 0.5, the signal was passed through, but it's smaller. It's attenuated. So gating lets us control what passes through and what gets blocked, which is really useful. Now, in order to do gating, it's nice to have a value that you know is always between 0 and 1. So we introduce another squashing function. This will represent with a circle with a flat bottom, and it's called the logistic function. It's very similar to the other squashing function, the hyperbolic tangent, except that it just goes between 0 and 1 instead of -1 and 1. Now, when we introduce all of these together, what we get, we still have the combination of our previous predictions and our new information. Those vectors get passed, and we make predictions based on them. Those predictions get passed through, but the other thing that happens is a copy of those predictions is held onto for the next time step, the next pass through the network. And some of them, here's a gate right here, some of them are forgotten, some of them are remembered. The ones that are remembered are added. Time happens is up them. Those what we get. Now, when we introduce all of these together, what we get, we still have the combination of our previous predictions and our new information. Those vectors get passed, and we make predictions based on them. Those predictions get passed through, but the other thing that happens is a copy of those predictions is held onto for the next time step, the next pass through the network. And some
Yeah, I don't quite understand this part. The reason why I don't understand it is, so the prediction goes out of so the neural network makes a prediction, but then it seems as if, and this is the memory section, so it's predictions we go into memory, but it seems as if there are two places that it enters the memory from. One is from here, and then one is from there. So yeah, I'm very. Oh, unless this is the memory section, and this is what controls forgetting. Oh, okay, wait, never mind, I think I got it.
Some of them, here's a gate right here. Some of them are forgotten, some of them are remembered. The ones that are remembered are added back into the prediction. So now we have not just prediction, but predictions plus the memory. Some of them are passed through the network. And some of them, here's a gate right here. Some of them are forgotten, some of them are remembered. The ones that are remembered are added back into the prediction. So now we have not just prediction, but predictions plus the memories that we've accumulated and that we haven't chosen to forget yet. Now there's an entirely separate neural network here that learns when to forget what. Based on what we're seeing right now, what do we want to remember? What do we want to forget? So you can see this is powerful. This will let us hold on to things for as long as we want. Now you've probably noticed though, when we are combining our predictions with our memories, we may not necessarily want to release all of those memories out as new predictions each time. So we want a little filter to keep our memories inside and let our predictions get out. And we add another gate for that to do selection. It has its own neural network, so its own voting process, so that our new information and our previous predictions can be used to vote on what all the gates should be, what should be kept internal, and what should be released as a prediction. We've also introduced another squashing function here. Since we do an addition here, it's possible that things could become greater than 1 or smaller than -1, so we just squash it to be careful, to make sure it never gets out of control. And now, when we bring in new predictions, we make a lot of possibilities, and then we collect those with memory over time, and of all of those possible predictions, at each time step, we select just a few to release as the prediction for that moment. Each of these things, when to forget and when to let things out of our memory, are learned by their own neural networks. And the only other piece we need to add to complete our picture here is yet another set of gates. This lets us actually ignore possible possibilities as they come in. This is an attention mechanism. It lets things that aren't immediately relevant be set aside so they don't cloud the predictions in memory going forward. It has its own neural network and its own logistic squashing function and its own gating activity right here. Now, long short-term memory has a lot of pieces, a lot of bits that work together, and it's a little much to wrap your head around it all at once. So what we'll do is take a very simple example and step through it just to illustrate how a couple of these pieces work. It's admittedly an overly simplistic example, and feel free to poke holes at it later. When you get to that point, then you know you're ready to move on to the next level of material. So we are now in the process of writing our children's book. And for the purposes of demonstration, we'll assume that this LSTM has been trained on our children's books, examples that we want to mimic. And all of the appropriate votes and weights in those neural networks have been learned. Gets blocked here, and the word saw gets sent out as the prediction for the next time. Saw, and we get a new learning and attention is that we were maintaining based on I want to hold on to the vote for not Doug, vote for the step language, and I want to another signal information page to dig into it more. But this is, if you're curious what LSTMs look like in math, this is it. This is lifted straight from the Wikipedia page. I won't step through it, but it's encouraging that something that looks so complex expressed mathematically actually makes a fairly straightforward picture. And for purposes of demonstration, we'll assume that this LSTM has been trained, all of the appropriate vote. So far, our story so far is Jane saw Spot, period. Doug is the most recent word that's occurred in our story. And also, not surprisingly for this time step, the names Doug, Jane, and Spot were all predicted as viable options. This makes sense. We had just wrapped up a sentence with a period. The new sentence can start with any name, so these are all great predictions. So we have our new information, which is the word Doug. We have our recent prediction, which is Doug, Jane, and Spot. And we pass these two vectors together to all four of our neural networks, which are learning to make predictions, to do ignoring, to do forgetting, and to do selection. So the first one of these makes some predictions. Given that the word Doug just occurred, this has learned that the word saw is a great guess to make for a next word. But it's also learned that having seen the word Doug, that it should not see the word Doug again very soon, seeing the word Doug at the beginning of a sentence. So it makes a positive prediction for saw and a negative prediction for Doug. It says, I do not expect to see Doug in the near future. So that's why Doug is in black. So this example is so simple, we don't need to focus on attention or ignoring, so we'll skip over it for now. And this prediction of saw, not Doug, is passed forward. And again, for the purposes of simplicity, let's say there's no memory at the moment, so saw and Doug get passed forward, and then the selection mechanism here has learned that when the most recent word was a name, then what comes next is either going to be the word saw or a period. So it blocks any other names from coming out. So the fact that there's a vote for not Doug gets blocked here, and the word saw gets sent out as the prediction for the next time step. So we take a step forward in time now. The word saw is our most recent word and our most recent prediction. They get passed forward to all of these neural networks, and we get a new set of predictions. Because the word saw just occurred, we now predict that the words Doug, Jane, or Spot might come next. We'll pass over ignoring inattention in this example, and we'll take those predictions forward. Now, the other thing that happened is our previous set of possibilities, the word saw and not Doug, that we were maintaining internally, get passed to a forgetting gate. Now, the forgetting gate says, hey, my last word that occurred was the word saw. Based on my past experience, then I can forget about, I know that it occurred, I can forget that it happened, but I want to keep any predictions having to do with names. So it forgets saw, holds on to the vote for not Doug, and now at this element by element addition, we have a positive vote for Doug, a negative vote for Doug, and so they cancel each other out. So now we just have votes for Jane and Spot. Those get passed forward. Our selection gate, it knows that the word saw just occurred, and based on experience, a name will happen next. And so it passes through these predictions for names. And for the next time step, then, we get predictions of only Jane and Spot, not Doug. This avoids the Doug saw Doug period type of error and the other errors that we saw. What this shows is that long short-term memory can look back 2, 3, many time steps and use that information to make good predictions about what's going to happen next. Now, to be fair to vanilla recurrent neural networks, they can actually look back several time steps as well, but not very many. LSTM can look back many time steps and has shown that successfully. This is really useful in some surprisingly practical applications. If I have text in one language and I want to translate it to text to another language, LST to phrase, or even in some cases, and just using the bits and pieces, just can use fit for robotics is nothing more than an agent carrying out an action many time steps down the line. If you're curious what LSTMs look like in math, this is it. This is lifted straight from the Wikipedia page. I won't step through it, but it's encouraging that something that looks so complex expressed mathematically actually makes a fairly straightforward picture and story. And if you'd like to dig into it more, I encourage you to go to the Wikipedia page. Also, there are a collection of really good tutorials and discussions, other ways of explaining LSTMs that you may find helpful as well.
Test. Numbers. So the network looked at a lot of house numbers and it came up with a way of painting them. And so these are not in the training data, these are made up house numbers from the model. None of these are actually in the training set.
So these are like made up?
These are made up, yeah. They look quite real, but they're actually made up from the model.
Okay, so I kind of understand what he's talking about here, but there's still a lot of stuff that I'm fuzzy on, so let's just jump into Excel and see if we can build it. I am a little concerned though, because so this is the recurrent neural network that we created, or this thingamajigger here represents that recurrent neural network, and then these up here are other neural networks as well, and so we need to build those into Excel, then we need to train them. Yeah, all right, yeah, this might be a little messy, but we'll try it out. We'll see how it goes. If it's too messy and it just gets too convoluted, then we'll just jump straight into code, which I don't mind at all. But yeah, I mean, so can't I move? the heck? Is it a limit? It's a dumb whiteboard. But yeah, so essentially what an LSTM is if I pull up our recurrent, where'd I throw this thing? Okay, I think I lost it. Oh, here it is. Actually, you know what? Let me just draw a new one. So, actually, you know what? Let me just go through what he has, because I think this is a pretty good enough drawing. So, if we essentially, you know, our RNN is represented by this structure here, and so all we're really doing is we're just adding a few more gates to allow the neural network to have memory and hold information for longer in the future. So the current LSTM, you know, it only goes by what's current and what happened one time step before. Now, you know, you can build more layers into it and get it to maybe look two or like a few time steps back, but not really too many. And that's where the LSTM comes in, because it incorporates something called a memory gate. So, you know, that controls what it keeps in mind for many time steps in the future. It also controls what to ignore, and it also has a selection gate as well. So it can start filtering out predictions that may not be appropriate. So it's like an RNN, but just a more advanced version of it that allows us to remember more of the past and what has happened in the past, and then take action based off of that. So let's try building it out in Excel. I have like 15 minutes, so I'm definitely not going to finish it today, but let's at least try it out and see where it goes. Okay, so what I'll do is I'll actually just pour through and see if I can find a working example of someone who's done this in code without libraries. So I found a few pieces of code, and it seems as if how they've structured it is that they have their RNN library, and then LSTM is built into that RNN library. Or LSTM is just an extension of that library. How in the world does backprop work for LSTM? I thought this was gonna be easy. Holy cow. I actually don't understand anything. Alright, let's just start building it out and we'll figure it out along the way. I'll build for about half an hour or so. And that will be that. So let me... So what I'm doing right now is I'm just duplicating the RNN that we had. The reason being is because so I was just thinking about like moving my camera over here and then like, taking a look at the screen there, but whatever, it's fine. Reason being is because most of all the code that I'm taking a look at, an LSTM is essentially just an extension of an RNN, which makes sense based off of Brandon's explanation of an RNN. So I'm just gonna go ahead and I'm just gonna duplicate that. And that did not duplicate. Let's do that again. Make a copy. Make a copy. Okay, there we are. So now we're in our new RNN. Zoom in a little bit. It's easier to read what's going on the screen. Let's do that. Yeah, let's leave it at that. How far is too far when zooming in? Is that enough? Okay, let's do something like... Let me try this out and let me see what it looks like in post-editing. Or editing. Post-editing. So a couple of things we need. Let me go through this code line by line, see what I already have, and then build out new things that I don't already have, and then we'll just go from there. So I have our input. This is our input. We have our output. Okay, we have our learning rate. We have our recurrences, but we've physically built them out rather than here where it's just encoded in code. We have our learning rate. Our array for storing inputs. We don't need it for Excel. Array for storing cell state. Again, we don't need that for Excel. We already have it here. Oops, where is it? We already have it here. These are our cell states. An array for storing outputs. Again, we don't need that. That's already laid out here for us. These are all our outputs. Oh, wait, no, hold up. The difference between a cell state and a hidden state. Let me read through this. Okay, so I think I'm beginning to get a better understanding of it. I think that if we take a look at this, which is a much cleaner version of my, of my drawing, essentially what we're doing is we are. Can I use my pen? Or will that movie? Oh, yeah, I can use my. Oh, beautiful! I never knew that. So what we're doing is we're replacing this hidden state with an LSTM, and that's essentially what it is. So again, this whole thing here is the recurrent neural network. And all we're just doing is we're just replacing this with a LSTM cell. And an LSTM cell is essentially, this is just a much more complicated way of looking at what Brandon did. But I guess that's it. I don't know why I'm so confused. Maybe it's just putting it in code is just kind of confusing me a little bit. But yeah, so you have what controls your inputs to the cell state. The cell state is essentially just our long-term memory. So you have the inputs to the cell state. You have something that controls whether or not that cell state forgets things in the future. And then you have the output, which actually starts selecting stuff from memory, from your long-term memory, and adds them to the output. Okay, feeling more confident. Let's go back to Excel. Okay, I'm sorry, I need to, let's spec 150. I need to see some more of my screen. Okay, so I mean we don't need this because again in Excel you don't really need to define arrays. You just put information wherever you want to put it. But now I know what the cell state is for. I know what the output is for. I know what the hidden state is for. I know why we have a forget gate, why we have an input gate, why we have a cell state. Oh, okay, this is for storing cell states. We have our cell state, we have our output gate. And then you think you understand something until you actually have to build it out, and then you realize you have no clue what the hell you're talking about. Okay, so essentially this section here is what needs to be, what I need to change. So in this section, Go ahead and add a few columns here, new columns. Some of these columns, what I'm going to be doing is actually no, let me keep 150. I actually have no plan for this. This is very, very messy. It's going to be a very rough log, but I actually have no clue how to do this. LSTM. There's the RNN part. And then I'm just going to have a, just so I at least know when the LSTM part starts. So in here we have our input, we have our inputs. Okay, I have 15 minutes. Let me just build out something. If it doesn't work, we'll redo this tomorrow. I just need to start building something out. So let me first build out our cell state. So just call this cell state. So the cell state itself is the memory for long short term. So before I do a cell state, let me just do our input gate. I'm just trying to figure out, guys, I'm very, very lost right now. Fine, screw it, whatever. I'm just gonna do whatever comes to mind, whatever I can muster and figure out. This doesn't make any sense whatsoever. Input, input, output, output. Input size, input size. Okay, so let me just go line by. So what's our input size? Our input size is we're inputting 4, right? That's our input size. So it's an array. We have 4 columns. We're inputting. Our output size. Our output size is 4. So we have 4 bits that we are inputting for each of the letters that we have in our alphabet, and then in our output, what we're doing is our final output. What we're doing is, the hell is this stupid thing? What we're doing is we're also outputting 4 letters of the alphabet. So that's that. So when it says here that our when it says here that we have our input gate is our output plus input. What the heck? Okay, so that means that it's 4 rows and 4. What's your problem? Oh, actually, no, you're right. What have I done? Okay, so something like that is our input gate. So we have the input gate, and pretty much all the other gates are like this. So let me just go ahead and copy. Oh my god. Let's go ahead and copy this. We have our input. Is the cell state like that too? So we have the cell state. We have our forget gate. Then we have our output gate. So I need one more of these guys. Okay, we now have our different gates. So how the hell does this work? I at least want to get forward prop at least halfway done or something like that before I move on. Okay, so what it does is that it feeds the LSTM with the current X and the prior X. This is, I think, what I've done. Actually, okay, so I need more space. And what I'm going to do is I'm just going to move these guys up to these positions. And this code is very, very messy. I can't follow it. Okay, 4 more minutes. Let's see what we can do in 4 minutes. Okay, so in time step 1, we have our current input. I'm so confused. Don't we start with the input gate? Or why do we start with the forget gate? Fine, whatever. I guess we're starting with the forget gate. I really don't have the time for this. It probably makes sense at the very end, so just go ahead with what they have now. include at the very end. So this is input state, and then we have the cell state. Right, input gate. Then we have a cell state, and then the last one we have is the output. Okay, so what we do apparently is we take our forget gate, we multiply our forget gate, which is a 4x8 matrix, by self.x. And so self.x is getting, okay, so actually we do input into LSTM. So input into the LSTM will be the output from the previous time step. This makes no damn sense. Okay, but like this makes no sense because my hidden state is this, and this has a vector size of 3. My actual output Okay, you know what? Screw this. I'm gonna look for a better resource. I really can't understand anything these guys like. I cannot understand this. I look for a better resource. I guess we just wasted an hour this morning. I'm actually kind of pissed, but whatever. So I'll look for a better resource, and I will see you guys tomorrow. Because I'll probably spend most of the night either looking for a resource or trying to edit and make sense out of this useless vlog for today. But whatever.